Isotopes are versions of the same element that differ in the total number of neutrons. So what you actually see is a weighted average. We calculate the weighted average based upon the natural abundances. So as an example, the element strontium has 4 different versions of strontium. There's one that has a mass number of 84, that has an abundance, as you can see here, of 0.5%. Mass number 86, that abundance of 9.9%, a mass number 87 with abundance of 7%. And finally, the 4th version of strontium, differing in the number of neutrons, has a has a natural abundance of 82.6%. So the number you see in a periodic table is 87.62. How do we get that number? Well, all 4 versions contribute to this. Okay, the mass at 84 contributes 0.5%. So the mass at 84 contributes 0.5%. So I'm going to move the decimal place. 0.5% is nothing more than 0.005. So 0.005 multiplied by 100 is 0.5%. So 0.005, just converting the percentage to a number. We add that to the mass number 86, which has a natural abundance contribution of 0.0099, okay, which is the same thing as 9.9%. The 3rd version of strontium is the 87. So that mass number 87 exists as a natural abundance, or exists 0.07% of the time, 0.07, which is the same thing as 7% of the time. So that also gets added to our number that we see in the periodic table. Okay, finally, our 4th version is the mass number 88. So the mass number 88 has a natural abundance contribution of 0.826, which is the same thing again as 82.6%. So we'll add all of these up and get our final answer. The units here are going to be AMU, standing for atomic mass units. They can also equal to grams per mole. Remember, it's the contribution of each of these, which is the number that you see in the periodic table. 87.712, and that's going to be in atomic mass units, AMUs. So 87.712, if we grab something from the periodic table, we get a value of 87.62. That's very, very close. In fact, we can actually calculate how close it is. By doing that, that would be the percent error or percent accuracy, provided that this 87.62 that we got off from the textbook reference is accurate. So to get the percent accuracy and the percent error, well, first we'll calculate the percent error. We'll take our number we calculated, 87.712, minus the known. The known is 87.62, using that as the reference, and dividing it by 87.62, which is the known, the reference. We can take the absolute value of that to remove any negative number, and when we do that, we'll get an answer of 0.0010 or 0.1% error. So 0.1% error based upon the textbook value of strontium, which was 87.62. How accurate is this? So that's the percent error. We can also figure out how accurate it is. So that's going to be 1 minus 0.0010, which is about 99% accuracy. So 99% accuracy, 0.1% error, very, very close. The isotopes, you see the isotopes, each one contributes to the weighted average. So the weighted average is what you see when you read off the mass number in the periodic table, which comes from isotopes.